Okay, sorry about that. Forgot about the recording. So start again. Hello, everyone. We today have Alberto Marchionni as our speaker, who's a Fermilab researcher and part of the DUNE collaboration. Alberto has also previously worked at CERN at INFN in Florence, and he has been part of many other experimental collaborations such as Lab L3, Microboon, Nomad, NA61, and Minus. So it's all yours.
Well, thank you for the invitation. And I'm going to remove the Zoom stuff here, move it away. So I'm going to talk about DUNE. DUNE stands for Deep Underground Neutrino Experiment. I don't know why it doesn't. Sorry, I can't change a slide. Okay, sorry for this. So the Deep Underground Neutrino Experiment is supported by what we call the Long Baseline Neutrino Facility. And you see here a sketch of the full project. So we start producing neutrinos at Fermilab, and they are sent to South Dakota over a 1,300-kilometer baseline. The detector is on axis, so we see a wide-band neutrino energy spectrum, and we have detectors in South Dakota, far detectors using liquid argon technology, and I'll go through some details about this. And these detectors, they are about 1 mile underground. And in addition, there is a near detector in this position, which provides control of all systematic uncertainties. So the DUNE collaboration is getting large. It's composed by something like 1,400 collaborators. There are 37 countries and 206 institutions. And we were able to fill the CERN auditorium in January. So let me go through the physics program of DUNE. So first of all, we have a long baseline wide-band neutrino beam, and this will allow measurement of CP violation and determination of the mass hierarchy in a single experiment using the spectral information. The deep underground location allows access to astrophysical neutrinos. So we have potentiality to observe supernova neutrino burst, and we are sensitive, as you will see, to the electron neutrino component, and this is unique to DUNE. We have possibility to observe atmospheric neutrinos and capability for tau neutrino identification. And we will be sensitive also to solar neutrinos for a potential detection of the HEP flux. The massive detector, as you will see, has excellent tracking and calorimetric information. So we can do baryon number violating processes, for example, proton, which goes to new bark A+, and search for neutron, anti-neutron oscillation. In addition, the long baseline and the possibility to tune the beam even to higher energy it gives access to tau neutrino appearance and also to non-standard interaction searches. So let me go quickly through the formalism of neutrino oscillation. I am an experimentalist, I'm not a theorist, but this is the unitary matrix which with this matrix, we are able to express the flavor neutrinos as a function of the mass eigenstate of the neutrino. You see that this matrix has 3 mixing angle and a phase, which is this delta Cp. So this matrix simplifies enormously if we go to 2 neutrino oscillation. You have just to look, for example, at this part, and everything can be expressed simply by just 1 mixing angle. But when you go to 3 neutrino oscillation and you try to compute, for example, the probability of a new mu beam, which is, what we are able to produce here at Fermilab, and how this oscillates in UE, you get this complicated formula. And if you look at this formula, you see that it's different for neutrinos and antineutrinos because you have to choose a minus sign here, and there is also this matter effect, which is expressed by this V, which is changing sign for antineutrinos. So in order to observe CP violation, which means to observe a difference of nu mu, which goes to nu E, versus nu mu bar, which goes to nu E bar, this actually, it gives access to CP violation through this term here. And you see that the matrix is quite complicated. The oscillation formula is quite complicated when you take into account the delta m square of neutrino oscillation, this factor A, which involves matter effect, the alpha, which is the ratio of delta m square for solar oscillation over delta m square for atmospheric oscillation, and alpha, delta, and A are sensitive to the sign of delta m square 3-1. But the fact that this oscillation probability, it depends by all these things, it gives you access both to the measurement of CP violation and to the measurement of the sign of delta m square 3-1, because you see things where delta m square 3-1 enters in the formula linearly, not quadratically, so you are sensitive to the sign of this, and so you can measure the ordering of the neutrino masses. And I will show you, graphically what this formula means later. So there's been a spectacular progress in the last 20 years in neutrino physics. And here you see versus the year number, the measurement of all the mixing angle and the 2 delta m square, which regulate neutrino oscillation. You also see that, in numbers, theta 2-3, which is the responsible for atmospheric and long baseline oscillation, is of the order of 45 degrees. Theta 1-2, which instead can be measured by solar neutrino oscillation or reactor neutrinos, it's about 34 degrees. And more recently, it has been measured theta 1-3, which it came out, fortunately, relatively large, 8.5 degrees. If you allow me to go back one slide, you will see that the term which is responsible for neutrino oscillation, it depends by the maximum of this Yarskog invariant, which is linear in sine theta 1,3. If this sine theta 1,3 would have been 0, there would have been no way, or, so small that it would have been impossible to measure, we would not have had access to the measurement of CP violation in neutrino oscillation. You also see from this picture that if you try to express the flavor eigenstate as a superposition of the mass eigenstate, and here the area of each square is proportional to the component of the mass eigenstate, you see that nu e is mainly nu1 and very little nu3, and this is due to the fact that theta 1,3 is quite small, while nu mu and nu tau, they have a higher component of nu3. So, but we are not done yet. If you look carefully at the measurement, you see two things. You see that there is still quite an uncertainty on the measurement of sine square theta 2,3. This is a collection of recent measurements. You see that the experiment of Fermilab, Minos, and Nova, they have this kind of dual thing, around a value of 0.5 for sine square theta 2,3. So it would be really interesting to know if theta 1,3 is exactly 45 degrees or not. But still, there is quite an uncertainty in the measurement of this value. And the other big uncertainty is on the measurement of delta CP. We only have very initial measurements by T2K, which are represented here by the black and the dotted line, and Nova, which has, these colored regions. When you do the full fit, if you have normal ordering for the neutrino masses, and I will explain what this means better in the next slide, the best fit for Nova is not where there is the best fit for T2K. They look, they have a small regional superposition, but here the measurements are in tension. For inverted ordering, the agreement is a little better, but you have to go to 90% confidence level for the T2K measurement. So, and you will see, that the measurement of delta CP is quite difficult, and so it's a matter of statistics, but it's also a matter of fully understanding all the systematics in the measurement. And this is what DUNE will address. So we have still open questions in neutrino oscillation. The first one, which is really important, also conceptually, is the neutrino mass ordering. Is delta m squared 3,2 positive or negative? So here I call it delta m squared 3,2 in the picture. I call it delta m squared atmospheric, but they are the same quantity. And this is essentially related to the fact to the ordering of the neutrino mass eigenstates. Is nu3 the heaviest or is nu2? We know from measurement of solar neutrino that the ordering between nu1 and nu2 is this one. But we don't know where nu3 is lying. So, and then is there CP violation in the leptonic sector, and how large is it? We do not have a good measurement of this. And the other thing is how close is theta 1,3 to pi over 2? This is essentially the same as asking, is U mu 3 equal to U tau 3? If you go back to the mixing matrix, you see it clearly here. So, you know, knowing if U mu 3 is exactly equal to U tau 3, it would be quite interesting also conceptually. It means there must be some kind of symmetry behind the mixing matrix. And the other general question is this metric, which is called Pontecorvo, Nakagawa, Sakata matrix, so PMNS matrix. Is it really unitary, or there is something else? Is there a new form that we should consider? And if you look at the measurement of this matrix, you see that the measure uncertainty in determining the unitarity of this matrix is the knowledge of these bottom components here, which are really hard to measure, U tau 1, U tau 2, and U tau 3. So let me go now to the DUNE, and so how we are going to proceed. Here at Fermilab, we are producing a neutrino beam, which is mainly composed of muon neutrinos. Given the knowledge of the mixing angle that we have today, you know, as this neutrino beam is progressing over the 1,300 kilometers to South Dakota, you will observe disappearance of muon neutrinos, appearance of new tau neutrinos, and a smaller appearance, so it's a subdominant oscillation of nu mu into electron neutrinos. And if theta 2,3 is would be exactly equal to 45 degrees, you would reach a point where all of your muon neutrinos would disappear, and you would only be left with muon neutrinos and electron neutrinos. And as you go farther, you know, you go up on the second oscillation, and you see the reappearance of new muon neutrinos. So in order to do this, you need a neutrino beam, if you do the calculation, which is centered about 2.5 GeV. And here you see the new mu spectrum with a beam which we are able to produce at Fermilab. And you also see the probability of oscillation of nu mu to nu e, which depends on the ordering of the neutrino mass. And you can see quite the large difference for a delta Cp equal to 0 degrees between normal hierarchy and inverted hierarchy. So for DUNE, this is a relatively easy measurement to do. If you stay with normal hierarchy and you want to measure delta Cp, you see that according to the value of delta Cp, you have different shapes for the probability of nu mu, which goes to nu e, but the difference between these curves, you know, they become smaller. So you need high statistics, which means a very large detector and a very powerful neutrino beam. So what we need to do, we need to build a detector which is capable of doing electron-neutrino physics. This has been done in the past. You go back to the Gargamel bubble chamber. It was using heavy freon, so you could see bubbles of the order of 3 millimeters. The radiation length was about, in heavy freon, it's about 11 centimeters, which means that you were able to sample an electron at the percent level of the radiation length. This The other detector, which was very capable in observing electron neutrinos, is NOMAD, and I was part of NOMAD. And there was also a participation by a group from Australia in NOMAD. I remember, the people I worked with. And you can see here, how well the electron neutrinos were identified in NOMAD. So the target was composed by light drift chamber. The density was only 0.1 grams per cubic centimeter. And the spacing, the readout, was such that we were sampling things at 2% of the radiation length for each chamber. But, nor the bubble chamber, nor NOMAD is extrapolable to detectors which have to be, of the order of 10 kilotons or more. NOMAD was only 2.7 tons. So in order to jump from this old detector to what is needed now, you have to use liquid argon TPCs. And I will show you that this technology allows you to build detectors of 10 kilotons or more. And in a liquid argon TPC, the radiation length is 14 centimeters. Given the way this detector works, you have a resolution of the order of 5 millimeters. And again, you can sample X0 at the percent, at a few percent level. So this is what you would need in order to distinguish an electron, as you see here in this picture, versus gammas, which are coming from pi zeros, that, the conversion length of gammas is related to X0, is actually 9/7 of X0, but sampling, with a small percentage of X0, it gives you the possibility to see that the gamma is not coming from the primary vertex, but is displaced, and also gives you the possibility to measure the ionization of the initial track that you see. And if the initial track is compatible with the EDX of a single particle, it's most probably an electron. But if you have the conversion of a photon where E plus and E minus are superimposed, you will see 2 times the EDX. So this is the measurement that you can do with the liquid argon TPC. I'll try to go fast here. So the technology of liquid argon was introduced, Alvarez already in 1968, was talking about that. Liquid argon TPCs were proposed by Carlo Rubbia in 1977 and by Herbert Chen in 1978. Herbert Chen unfortunately died young of leukemia, but he was also the person who essentially thought about the SNO experiment, which then was realized in Canada. So the properties that make this technology possible are the high mobility and low diffusion of electrons in liquid argon, the fact that liquid argon is a very good scintillator, and even if the liquid argon TPC, concerning the charge is low, the light is fast, you can go down to 10 nanosecond resolution, you can have a high readout granularity. So this detector is ideal for physics in the MeV to GeV range. And there have been many detectors operating in the last 15 years, starting from Icarus, Argonaut, Microboon, Lariat, Fermilab, Captain. It's another detector which has been built. And more recently, prototypes of DUNE which we call protodunes at CERN. So how does a liquid argon time projection chamber work? So you get a ionization of liquid argon. The electrons drift towards a detector plane, which is usually composed of wire planes. So what you record the time of arrival of these electrons as a function of time. So this is the axis time. And here you see an interaction, a V. And if you have multiple wire planes, you can reconstruct essentially these tracks. What you see here on the side is not a simulation, but this is a real event constructed with a prototype of DUNE, and you see a cosmic ray with deltas, and you also see the signals corresponding, to a channel. So it's a slice in this direction of these pictures. And you see that you have in the first two pictures, these are induction planes because the electrons, they go through the wires, but they are only collected, at the end on the collection plane. So the signals are bipolar, while once you get to the collection plane, you get unipolar signal. This information, it provides both tracking and also calorimetric information through the amplitude, through the height of these signals. So here you see pictures of the actual protodune detectors at CERN, and we have two of them. So CERN built an extension of the north area in order to be able, to locate these detectors. And here you see what one protodune looks like externally and what it looks like inside. So the size of this, it's about 7 by 6 by 7 cubic meters. And inside, you see a membrane which contains the liquid argon. The technology which has been used is the same technology which is being used by ships who bring liquefied natural gas. And actually, there are only two companies in the world who are able to produce these ships. And one of them, they went from ships building liquefied natural gas to liquid argon containers for us. And it wasn't easy, to convince them to do this, as you can imagine. We are not as rich as the people doing liquefied natural gas. So, but this technology, it works very well. We had two protodunes installed at CERN, and you see one of them, which is actually located here. This one, it has a drift length of 3.5 meters, and the readout is done with wire planes, which we call the APA, the anode plane assembly. There are 3 APAs here. These are objects which are each APA is 6 meters by 2.3 meters, and each APA has of the order of 15,000 wires. They are very difficult to build. More recently, we have developed a new technology where for the charge readout, we do not use wire planes, but we use standard PCBs. And I will show you how this works in the next slide. In this configuration, the drift is vertical, while here it's horizontal. And what you see here, this is, we are still finishing to install this module. This is the cathode, which provides two separate drift fields, one at the top with top CRPs and one at the bottom with bottom CRPs, which are not yet installed in this picture. So this CRPs means charge readout planes. And the idea is somehow simple, and it's a development of the thick gems. So you use perforated PCBs that you see in this picture here, and with two of them, you drift the electrons through the holes of these perforated PCBs. So at the bottom, we have what we call a shielding plane, which is not read out, which is followed by an induction plane. So the electrons go through here and they induce signal here. Then they go through the bottom of the second PCB and they induce signals there. And finally, they are collected on the top side of the second PCBs. So with this technology, actually, we were able to obtain these tracks. They were not done with the wire planes, but with this technology. Now, this looks simple. At the end, what you build are objects like this, which are 3.4 by 3 meters, and they look more complicated because you have to keep these two PCBs together, you have to collect signals and all of that. So, but the technology actually worked. And this is a big advancement because it allows not to have wires and to reduce the cost very substantially. So we had a first test in one of the protodunes using wire planes, and there was a test beam line which could shoot particles inside these protodunes. And here you see some pictures. So, and this is not simulation, it's real data. You see here how a 0.5 GeV electrons appears. This is a higher energy electron, is 6 GeV. You see how a stopping proton appears, and you see the ionization increasing and the Bragg peak at the end. And this is a very nice event of a pion doing charge exchange, a pi plus doing charge exchange, and you see the pi zero and the two gammas from the pi zeros. You also see by measuring the EDX, so if you plot the EDX versus the residual range of the track, so as you go from here, to the end of the track, you see that we are able to distinguish extremely well protons from muons. And we are working now on the kaons, and the kaons, it would be an intermediate curve between these two. So now let me say something about the Farsight facility. This is located 1.5 kilometers below ground in South Dakota. It was an old gold mine, and the company left. They gave essentially all the mine to the state, and we were able to use it. So we are building 3 very large caverns. So what we call the North Cavern and the South Cavern. Each one of them has one detector, but the caverns are built to house 4 17.5 kiloton detector modules. If you look at the size of these caverns, they are huge. In the middle, there is a central utility cavern where, you have all the cryogenics in order to maintain the liquid arc. And the neutrino beam from Fermilab is coming from this side, so it goes, you know, to essentially to west. So this is the status of the advancement of the excavation. I'm sorry if you, well, now you can see it. So we have done 59.7% of the excavation, and you see here the north cavern. You see two different machines, one which removes the rock, the other one which is drilling and making holes where you put dynamite, you know, and then you explode and so on. So it's clearly quite a construction to build a detector like this, and there is an important part of the project. So the far side detectors, as I said, DUNE will comprise 4 far detector modules. The collaboration currently focuses on delivering 2 modules by 2030. So there is the one which we call FD1 horizontal drift, which is the one which has anode wire planes readout. And you see it here. There are 3 rows of wire planes for a total of 150 APAs, and 2 cathodes in the middle of each planes of wires, with a drift length of 3.5 meters. And here you see a picture of an APA, and in order to reduce the number of readout channels, the diagonal wires are wrapped around. And then there are ambiguities, but not that much, because they intersect the vertical wires only once per phase. And the second detector is based instead on the CRPs, the charge readout planes, and which are located at the top and the bottom of the cryostat. These objects, I'm sorry, I didn't write it, but they are 60 meters long. And here there is a cathode in the middle, with these squares are photon detectors, which are placed on the side of the detector and also over the cathode at 300 kilowatts. And there is all a technology to make this work. And the drift length, in this case, is 6.5 meters. So this detector is substantially cheaper than the other one. So CERN is part of the DUNE collaboration and is providing, in addition to some detector components, is providing the 2 cryostats. And here you see that the fabrication of the cryostat, which is lots of steel on the outside, is in progress. This is a company in Spain, and you know, they are already producing the parts. So now let me go quickly to the near site facility. You see that the near site is quite complicated too. So we have a very high intensity primary protons hitting a graphite target, and the protons are brought over a hill, and then they bend down to an angle of 5.8 degrees. There is a target here, and then there is a decay pipe, which allows pion to decay and to produce neutrinos. The beam power is initially 1.2 megawatt, but upgradable to 2.4 megawatt. And the Fermilab is upgrading the old LINAC, which was the LINAC of the beginning of Fermilab, with what we call PIP2, which is a LINAC with superconducting cavities that will allow to reach 1.2 megawatt. But I have to say that the current accelerators, Fermilab, who are providing beam, for example, neutrino beam, for the NOVA experiment, they already reached 900 kilowatt of beam power, which is really a record. So the neutrino beam line, it has three focusing elements. You see here 1, 2, and 3, which we call horns. You know, that's the name which was given to this device, you know, by CERN, essentially, who invented the horns. And the beam line has a slope of 5.8 degrees. The shape of the horns, it was optimized using a genetic algorithm in order to maximize sensitivity to CP violation. And as I said, the decay pipe is 194 meters long with a diameter of 4 meters. And here you see a shape of the neutrino beam flux. So this is the flux, is not interactions. And you see how flat it is here, because this is real, and this is good that it is this flat. This is what we were aiming for in order to cover the first oscillation maximum, which is at about 2.5 GV, and possibly reach the second oscillation maximum, which is at 0.8 GV. And you will see later more pictures. So, as I said, the near site has a near detector complex in order to measure the neutrino beam rate and the spectrum. So we have to predict to the far side the unoscillated spectrum and see how the oscillations, you know, modify the spectrum. I say complex because it has three main detectors: a liquid argon detector to measure neutrino interactions on argon, as in the far detector. The technology is slightly different, but I don't have time to go through. There is a muon spectrometer to measure muons coming from interactions from this detector. And these two detectors are movable on the site up to 30 meters. This is in order to measure very well the neutrino beam. And you learn a lot by going off axis, and you are able, like this, to really predict very precisely what the neutrino beam is at the source. And then there is an additional detector that measures the stability of the neutrino beam and is capable of measuring neutrino interactions on different targets. And this is a superconducting magnet. It's actually the Chloe superconducting magnet from Frascati, and it will be equipped with straw tubes. It will become a detector which functionally is very similar to the NOMAD detector. So, as I said, initially, the DUNE collaboration will provide two 17 kiloton liquid argon modules, but as you will see, we are also thinking and making plans, concrete plans, for two additional detector modules and the beam upgrade to larger than 2 megawatt, and also a more capable near detector, which is a replacement of the muon spectrometer by a high-pressure gas argon TPC. So now let me go to the physics that we can do with this device. So what you see here, let me move this just a moment. So what you see here, you see the probability for nu mu, which goes to nu e, for normal ordering and inverted ordering, and for anti-nu mu, which goes to anti-nu e. And you see that the shapes are quite different for normal and inverted ordering, and this is good because it means this will be an easy measurement. And as you go from neutrinos to antineutrinos, they are kind of inverted. This plot is quite similar to this one, and this is similar to that one, but not exact. So the mass ordering and the CP violation induce different shapes in the oscillation probability of electron and electron neutrinos and antineutrinos. And DUNE, using a wide band beam, has unique capabilities to measure the shapes. And at the end, this is what you measure. So this very nice and oscillation pattern, well, you're not going to see exactly this because you have to do the convolution of the oscillation probability with the neutrino beam flux and the cross-section, which depends on the energy. So when you do all the calculation, you see that for nu mu and nu mu bar, you can see the first, and the second oscillation maximum. So you see here, this is, you have to go at the minimum of the nu mu and nu mu bar, so which is 2.5, and then the second oscillation is about 0.8, but you have very nice measurement of nu mu disappearance, and then you have nu e and nu e bar appearance, and you see these were simulated for CP violation delta CP equals 0, you know, the points, but you see the difference, you know, for the different values of delta CP. At the end, what you have to do, you have to do a combined fit of nu e bar, nu mu, and nu mu bar, and get out at the same time the mass ordering and the delta CP. And I'm about at the end. So you see here the sensitivities of DUNE for low exposure. The first two plots are for the determination of the neutrino ordering, and the left plots are for delta CP. And if you look carefully at this picture, you will see that DUNE will unambiguously resolve the neutrino mass ordering at 3 sigma using, 66 kiloton megawatt year exposure. So this is the product of the beam power times the mass of the detector times the length, that you take data, and you reach 5 sigma at 100 kiloton megawatt years. And if you want to convert this in years, you have to divide by 1.2, which is the beam power, and 20, which is going to be, it may be maybe 10% higher than 20 kiloton, but the fiducial mass of the two detectors. So you will reach 3 sigma in less than 3 years. For CP violation, it is harder. So if delta CP is maximum, minus or plus pi over 2, you can reach 3 sigma with 100 kiloton megawatt years. And then you can try to see how the sensitivity goes for longer exposure, which is expressed here in this plot. The red curve is for a delta CP of minus pi over 2, which is actually the preferred value by T2K, but not by NOVA. This cyan curve is for covering 50% of the delta CP values, and the green curve is for 75% coverage of the delta CP. So if you want to cover 75% of the delta CP values, you have an exposure of almost 1100 kiloton megawatt years, which is about 14, well, it becomes 15 years if you go with phase 2, so an upgrade to 4 detectors and an upgrade of the beam power by a factor 2. It's almost unreachable if you stay with phase 1, because the 15 years, they become 60, which is, really too long time for the experiment. But we think that this detector, will operate for something like 30 years. And you see here also what you can achieve in the measurement of θ13, and this is θ13 versus CP violation, and this is delta M square versus sine square θ23. So the simulations for DUNE are the curves. The yellow region is what is given by a recent fit of all the measurement. So you can see how you improve, in particular, how much you improve. You won't improve much, the measurement of θ13, because that has been measured very accurately by Diabei in China. But you are going to improve on the measurement, obviously, of delta CP, but also on sine square θ23. And you will know if it is exactly 0.5 or if it's close to it and by how much. Let me just say something on the low energy events in DUNE. So DUNE has sensitivity mainly to electron neutrino events. So here you see how these neutrinos, it can be whichever flavor, because this is new electron elastic scattering. So you will see short tracks, of a couple of centimeters for a 10 MeV electrons. But there is another reaction which is possible to observe in liquid argon, which is nu E over argon 40, which gives an electron plus an excited state of potassium 40. So for this reaction, which has a much higher cross-section than this one, you will see the electron, which is, the small track here, but it will be accompanied by a de-excitation of the potassium 40. So you will see blips due, to the gammas from this excitation of potassium 40.
Alberto, sorry to interrupt you. We have 5 minutes.
Yeah, I am at the end.
Thank you.
I'm at the end. So for the supernova burst neutrinos, so as I said, DUNE has unique sensitivity to the nu E components, and this is what you expect to see. So at the neutronization state, if there are no neutrino oscillation, the neutronization state, it gives electron neutrinos, and DUNE will be capable to measure those. But once you add the oscillation, if the mass ordering is the normal one, this peak will disappear completely. If the ordering is inverted, it will be reduced. And here, so you're going to see, for the 3 different cases, what you will see in terms of nu E's. And this other plot, it gives the sensitivity as a function of distance. So for a supernova exploding, in our galaxy, for just one 10 kiloton detector, you are going to observe from 100 to few hundred interactions, and that will be multiplied obviously by 4 once you have the full 40 kiloton. This band, they represent the theoretical uncertainty on modeling the supernova. So these measurements, they would be very important. It would be very exciting to see one of these neutrino bursts. And we hope that in 30 years of running the experiment, we'll be able to see one of them. So my conclusions is that there has been an amazing development in liquid argon technology, I would say over the last 40 years, because Carlo Rubbia and even Herbert Chen, they started the late 70s, assembling something. But during the last 10 years, there's been, an increased rate of development. The other thing which is very important is that there is a hands-on experience and an amazing performance of high-power neutrino beam lines in the last 15 years. This happened at Fermilab, but not just at Fermilab, at J-Park in Japan, and also at CERN when they developed the neutrino beam from CERN to Gran Sasso. Unfortunately, at CERN now there is not anymore neutrino beam. And the people working on neutrino beam, from all these three places, they have meetings where they discuss openly, how to build these neutrino beams, which are really hard to build and to maintain. The excavation of the DUNE far side caverns, as I said, it's about 60% completed. This is extremely good. And while two DUNE detector modules are fully defined and, as you have seen, already prototyped, well, we are thinking about the other two, and we may take advantage of new developments. For example, use pixelized liquid argon TPCs, and there have been also, prototypes and tests of an optical readout TPC. I have no time to go through this, but this is extremely interesting. So DUNE, combining the long baseline, the wideband neutrino beam, and the liquid argon detector, allows simultaneous measurement of the mass ordering, delta CP, and the parameters, all the parameters of the three-flavor oscillation. The deep underground location provides capability to study low-energy neutrinos. I showed you example of core collapse supernova neutrinos, but we are also thinking about solar neutrinos in order to measure, the upper end of the boronate neutrinos and the HEP neutrinos. But DUNE also, but I was not able to cover in this talk, has also potential for baryon number violation searches, both proton decays, but also neutron, anti-neutron oscillation. If you get one of these events, neutron, anti-neutron oscillation with, annihilation of the anti-neutron inside the nucleus, it gives a spectacular event in liquid argon. And we also, by increasing a bit the neutrino energy, which is possible, we have a unique capability to produce a new tau beam above the charge current threshold. You have to go to neutrinos above 3.5 GeV, and we have unique sensitivity to new tau appearance. So thank you very much for listening.
Thank you, Alberto. That was great. Do we have questions? Yes, Bruce. Teresa, sorry.
Thanks.
Bruce was just.
Very nice talk. I had a question regarding the actual building of the experiment underground. I assume you have to do a lot of it in situ, as these are huge cryostats and the access is, there's not that much space to go underground in South Dakota.
Well, there is, so the access underground is clearly a very important one. And at the beginning of the project, and it delayed the project, was that we had to refurbish completely the shaft, because it was built, I think, probably middle of 1900. It was a wooden structure, which was, it wasn't safe. So all of this has been replaced with stainless steel. And not only, you know, the shaft, but also all the machinery to bring the cage up and down. Clearly, building these detectors underground is quite complex. And I'll tell you, so we had to do a test, and we have done a test. So if you look at the APAs, so as I said, the APAs are quite complex object because they have about 15,000 wires, and each APA is 6 meters by 2.3 meters, and we had to find a way to bring it underground. So we did a test, and the APA do not fit inside the cage of the elevator, but they are hanged at the bottom of the cage. And by operating slowly the elevator, we are able to bring an APA at the bottom and then back up without breaking it. That was quite good. So, but clearly there is lots of logistics. You know, once we come to installation, that shaft, it will work continuously for 24 hours a day. But, you know, there is, I think on Sunday, there is a half a day for maintenance of the elevator already planned. Did I answer your question?
Yeah, sounds challenging. Thanks.
Yeah, it's challenging. Everything is very challenging, but also exciting.
More questions? Yuki?
Hello, thank you very much for the nice presentation. I would like to ask whether you have a plan for using your detector as a kind of observatory, like, you know, Super Kamiokande or Hyper-K will do the proton decay or atmospheric neutrino measurements. So I was wondering if you have any kind of similar plan.
Yes, you know, personally, I've been working on this project for 10 years. I would say the first 5 years I was working on the neutrino beam. The next 5 years I've been working on detectors, both on APA and CRPs. But now, you know, so I am, if you want, a beam person, but I'm getting more and more interested in the physics without beam. In particular, proton decay, observation of atmospheric neutrinos.
Yep.
And as you can find, you know, I didn't put a reference, but we have a paper for reach in proton decay. But the collaboration feels that we need to look at it better and try to improve our reach.
Yep.
So, and the problem, I can tell you, you know, honestly, what it is. Reconstruction in liquid argon, as you can imagine, is quite complicated.
Yep.
Okay, so we see that, you know, once you have to reconstruct something like this, you know, you cannot do like an old bubble chamber that, you know, you put this on a scanning table and you measure the position of every heat. You have to do it with an automatic program. And we are improving on this a lot, using also neural networks and whatever. And we need to redo a study for proton decay that takes into account the recent development and the improvements in liquid argon reconstruction. So this is one of the things that we are looking at. And there are studies also for atmospheric neutrinos and also for the observation of new taus. But this is work in progress. So, but we want to operate as an observatory. And let me say that a detector with this granularity and capabilities, you know, of this size has never, this is the first detector underground. So we have to be open to new things that we may observe. And, you know, whatever we observe in the time that there is no beam, which is most of the time, because, you know, a beam spill is only 10 microseconds every 1 or 2 seconds. So during that time, we will acquire a lot of data and we will analyze it. But the development of the software, you know, is still going on, and I'm sure it will go on for many years. So, as Gabi said, I worked in L3. So, and something used to say, I have never seen an experiment that failed because of the software. So we think that we have the hardware right, and the software, we will make it work.
Thank you. Sounds really exciting.
More questions? If not, thank you again, Alberto. That was great.